Folks, let's pick up again with our electronic systems, and we'll cover the last section. So last time we were talking about transistors. We had BJT transistors there on the left. I suppose BJ transistors, since BJT transistor would be redundant, and MOSFET on the right. And so we want to pick up with our last section. So let's recall when we talked about in class low power and high power. Remember, high power is actuators, some of our sensors. I'm declaring it to be anything that's greater than 100 milliamps, greater than 5 volts. Low power is things like our microcontrollers, some of our sensors, some of our LEDs, that sort of thing, around the 10 milliamp, 3.3 or 5 volt range. And so we were using transistors in the last section to sort of bridge this gap between high power and low power. And we were going to use low power, such as our microcontrollers, to control high power, such as our actuators, either through amplification or switching. So either way works. It's a question of what we want to do. So why does this matter? Well, our mechatronic systems are going to require some sort of amplification or switching. Our electromechanical loads are going to have a low resistance. Think your DC motor's got a relatively low resistance. And so we're going to care about the current gain. And so we're going to use some sort of amplifier made out of transistors. And unlike your audio or your communication systems, we do care about DC, or very close to it. And we're also going to have different bandwidths than you might see in a purely electronic system, because our mechanical systems are rarely going to go above 10K. And I would say most of your mechanical systems aren't even going to go close to that. Depending on the size of your mechanical system, your large mechanical systems may have bandwidths that are down in the 1 hertz region or 1 to 10 hertz region. Your small ones, things like your piezoelectric actuation for very small things, could get up into the 5, 6, 8 kilohertz range, but we're rarely going to go any higher than that. So we want to look at how we're going to build our amplifier. And an amplifier could be just a transistor, or it could be some other circuit. But we want an amplifier to drive our system, our actuator, and we want to take those low power signals to drive that high power, which is why we need the amplifier. So one of the questions that came up before was, should we be using just a single transistor in linear amplification mode, i.e. acting like an amplifier, or should we be operating it in the saturation mode? And remember, your linear amplification for a BJT is going to control the motor speed with base current, or in a MOSFET with base voltage. If we did it with saturation mode, we'd be turning on and off the motor, and if we turn it on and off such that we turn it on more than off, we should drive it faster than otherwise. So which way would work better? Well, let's start by defining power and our efficiencies in terms of power. So our power, we're going to care about the input power. That's going to be our electrical power, and the output power, that's going to be also electrical power if we're just looking at the amplifier. If we include the motor in that, we can consider mechanical power. But in either way, we're going to be considering output power and input power, and we're going to consider the efficiency to be the ratio here. So how much power do you actually need? Well, depends on what you're doing. But your low power NPNs, like a signal level sort of NPN transistor, and again, I'm going to use a 2N3904 because that's what we have in lab, is going to have about a 200 milliamp current through the maximum current through the collector, and a maximum power dissipation of 625 milliwatts. And this is coming off the spec sheet. Always read the spec sheets. It's got a beta, an amplification of somewhere between 100 and 300. Now, if you compare that to a high power NPN like this 2N3055, that's going to be more like 15 amps and 115 watts. It's got a smaller amplification factor, only 20 to 100, but still, that's a lot of power. These are very different devices, very different packagings, as you can see, and very different requirements, though the one on the right, the high power, is definitely going to need a heatsink, whereas the one on the left isn't really going to need a heatsink. If you want to operate in the linear amplification region, you could use your Darlington pair like we talked about, and in that case, here's an example of a Darlington pair like a TIP 120. This is somewhere between those two with a 4 amp collector current and a 65 watt power dissipation. But look at that beta, 2500. That's a big amplification. So this would be one convenient way to use a very small signal to drive a much larger current because of that 2500 amplification. But let's look at the what happens if we don't use that, if we're not using a Darlington. And so if we're using just BJTs, no FETs on this one, we might use something like a forward reverse control, in which case we'll call this a Class B power stage. In this case, if I apply a high input voltage, then you can see that it's going to cause the Q push there, the transistor on the top, to act like a closed switch, and the one below the Q pole to act like an open switch, in which case you can trace that the current's going to flow from VCC down through Q push. Now it's got an open path to the VEE, so it's going to go instead through the load and to ground. If we go the other way, Vn is low, well then the Q pole is going to act like a closed switch, and the Q push is going to act like an open switch, and now the current is going to go from the ground around to VEE, which is presumably like a negative 15 volt supply. So we could do forward reverse with just switching. We can do amplification in other ways. And we can classify these. You might talk about a Class A amplifier. A Class A amplifier could be just a single transistor in the linear amplification mode. But look what happens. Again, you're going to get that amplification, which is nice, but you're not getting very good efficiency, only about 25% efficiency. We can do better than that. If we act with a Class B, a push-pull amplifier, then we've got a typical efficiency more like 70%. So if we go from linear amplification to switching, then right away we've got a much higher efficiency here. Now we lost the amplification, but still we got a much higher efficiency. But what if we want both and a high efficiency? We might go to a Class D amplifier. This is a very different sort of circuit, as you can tell. The Class D amplifier is going to have a lot more stuff in it. So let's see what we've got in there. We've got our input, that's the same as before, some sort of input signal. We've got our comparator, which might just be an op-amp. It could be something else. And we've got this triangle wave generator. And the triangle wave generator is going to be compared against the input. And so the result is going to be this PWM, a pulse width modulated signal, which is a square wave that's either high or low. And it's going to be more high than low where the input is higher, and more low than high where the input is lower. And we're going to run that into our switching controller. You notice we got this push-pull configuration of MOSFETs here. And so that's going to turn those MOSFETs on and off. So we're going to get amplification in that case. Well, maybe not amplification in this case that we talked about before. We're going to be switching on and off our higher power. But since we're only putting in high and low signals, we're only turning it on and off, we'll just get a larger version of that. And we run it through our low-pass filter. Well, it's going to filter out those sharp edges, and we'll get an amplified version of that original signal. So this has got transistors acting only in saturation mode. Only in saturation mode. So the transistors are just switching, but the net result of the whole thing put together is amplification. If we chose to put in a motor, say replace this low-pass filter with a motor like a DC motor, then we don't need the low-pass filter because the motor is going to act as a low-pass filter. And what's really nice is your efficiency somewhere between 80 and 95%. So we get a lot more efficiency, but we also added a lot more stuff to it. So you got to kind of make the call as to what's appropriate for you. We're going to do the Class D amplifier. We're going to do something very similar to this in lab for motor driver circuits. What's nice is that instead of having to worry about the triangle wave generator and the op-amp and the PWM and all that, a lot of that stuff is going to be built into your microcontroller. So for instance, the Arduino board is going to output a PWM for you. So you're not going to have to worry about that part. So where do we actually put these in relationship to actuators and sensors when we're running this? Well, you got a couple different configurations. If you've got a transistor that's going to be driving an actuator, a load, then we could put this in configuration 1 on the left or 2 on the right. And so you can see right away there's going to be a difference, and the main difference is going to be the voltage between the base and ground. And so we're typically going to want to use configuration 1. This is your preferred. configuration 2 here is going to have the limited voltage on the load because it's going to be limited by what the transistor can handle. And it's going to have the load influencing the switching behavior. So you're going to use 1. Yeah, almost always 1. And you might use something called an open collector. Occasionally what you're going to see is a digital device is going to have an output that's labeled as an open collector. You might see that in a particular package it'll have a symbol that looks something like that, a little diamond with a line, that'll be an open collector. And so in the open collector, the port that's visible is not something you're going to hook up directly to a transistor. It's instead going to be the collector of the transistor. And so in this case, we're going to wire up a pull-up resistor, as in it pulls it up to a power supply. So that's our pull-up resistor there, RP, pulling it up to 5 volts. And so what you can see here is that when the digital device opens or closes the transistor, current's going to flow from the 5 volts through the pull-up resistor through the transistor. But now the transistor is internal to the device. So if we've specified the pull-up resistor incorrectly, then we're potentially damaging the device rather than damaging an external discrete transistor. Is that a problem? Well, as long as we do it right, it shouldn't be a problem. Now, once we've got this pull-up resistor, that gives us this point that we can tie onto. And this point here, just like the ones that we saw before, is going to go high or low, depending on what's happening to the transistor. So if we just hook that up to a power MOSFET with a load, then we can drive this power MOSFET off of the open collector output with the pull-up resistor. So this is one configuration that you might see. There are other configurations where you use the open collector for some other fancy things, but this is one that you might see with a power MOSFET on the outside. Another implementation issue that you're going to worry about is an inductive load. And why do we care about inductive loads? Well, we want to drive motors, we want to drive solenoids. Those are all just coils of wire, and a coil of wire is going to be an inductor. So what happens with an inductor, though, is you have to remember that the equation of an inductor is that the voltage across the inductor is going to be the inductance, L, times the time derivative of the current. And so when you turn off the current, you have a sharp transition, you flip the switch off, that sharp transition in current, take a derivative of that, means it's going to be a spike in voltage. And a spike in voltage could be bad for your transistor. We call that kickback or flyback. And that's a bad thing. It'll damage your transistor. If you've got discrete transistors, that's fine. You pull out the transistor and you swap it out. But if you don't have discrete transistors, you might have just blown your motor driver. So how do we get around that? Well, we have to protect our transistors. So let's take another look here. Again, the voltage across the inductor, L, is the inductance times the time derivative of the current. So if the current is switching off at the base to the transistor, then the current is switching off, and this is a step, very sharp transition, is switching off at the inductor, and then based on the voltage law here, the voltage is going to see this spike, this downward spike. And the downward spike is going to correspond to a spike in voltage across the transistor from collector to emitter, and it may exceed the breakdown voltage, which would be bad, and you would damage the transistor. So we protect the transistor by adding what we call a freewheeling or flyback or kickback diode. Many names, same thing. Freewheeling, flyback, or kickback. And the diode provides a path for the current that doesn't go through the transistor so that it can just dissipate. So we put in, for every one of these transistors, we put in a diode, and the diode will protect the device. Notice the diode is pointing from the collector to the power supply. From the collector to the power supply. And you can see that the motor driver circuit on the right has got 4 of them built in. And in each one of these, the diode provides a closed path for the current to follow so that it can dissipate rather than spiking your transistor. So where are you going to see inductive loads in your project? Well, if something is going to move, then presumably there's going to be a motor of some sort, or a solenoid, or a relay. And so anytime you see a motor or a solenoid or a relay, well, it's an inductive device. And so you are going to need to have some protection. Does your motor driver that you buy off the shelf have a flyback diode built in? Maybe. Maybe not. You probably want to look into that, and I would say that if you have a question, just plan on installing them. It's not a big deal to add flyback diodes, and they're not going to hurt anything if it doesn't already exist. If it does already exist, it's not going to hurt anything either. So you might as well just add them if you're unsure. So the next thing we want to talk about is op amps. We're kind of all over the place in this video, I know. Op amps are very convenient little devices that do different operations like addition and subtraction and amplification and integration and filtering. Lots of different operations with an amplifier. And so an op amp is going to have, this is a schematic for a 741, which is just a cheap little op amp. It's going to have an inverting and a non-inverting port. That's the negative and the plus. It's going to have supply voltage, so you got to power this thing with a V plus and a V minus. Those are external supply voltages. And it's going to have an output EO. And so what happens is if the op amp sees that E plus is greater than E minus, the voltage at the positive terminal, the non-inverting terminal, is greater than the voltage at the inverting terminal, the output is going to be driven in the positive direction. If the voltage at the inverting is greater than the voltage at the non-inverting, output goes negative. So we're going to say that the output, EO, has a gain times the difference between E plus and E minus. These are voltages again. And we'll see that this is represented here as a gain in the graph, except what will happen is that there's these saturation regions. So if you say, boy, this gain is going to take me into a voltage above the supply, because I only supplied plus V over here, then, well, you can't get out more than you put in, so it's going to end up capping, and that's saturation. So what does it look like internally? Well, we model it like this. We model it as a resistance between E minus and E plus. So here's our difference. And a current source with a resistor at the output. And so sometimes you'll see the funny little description that it's modeled as somebody that sits there. There's our little person that's internal, that is reading the voltage difference between E minus and E plus, just reading that voltage difference and adjusting the current supply with VO such that that difference goes to 0. What's it look like actually? Well, it looks like this. You can see it's got a whole bunch of transistors in there and some resistors and some capacitors, and this is just a schematic of it. The actual silicon will look a little different, but you can see that in the blue we have the input differential amplifier. That's looking at those E plus and E minus, the non-inverting and the inverting inputs, and there's an output amplifier. And notice that it looks a little like our on the right, the red output amplifier. It looks a little like our push-pull amplifier from before. You might also see that configuration called a totem pole configuration with the transistors. So it's very complicated internally, which is why we simplify it quite a bit when we're talking about the function. We have some assumptions that we make. We say that the input impedance at the inverting and non-inverting ports is going to be infinite, but that the output impedance at the output is going to be 0. We say that it's got infinite open loop gain, infinite bandwidth, and no offset. But these aren't really true. They're just approximations that help us model things. Realistically, it's going to be close to that, but not perfect. So in this example, we've got V in connected to the non-inverting input. We've got V out connected to the output and a feedback loop from V out to the inverting port. And so we want to know, well, how do we work this out? Well, it's going to show you that when we apply the golden rules, we're going to see that V out is V in. And this is a follower circuit. But we need to know how to actually write this. And we're typically going to see that there's this negative feedback. This is our feedback. But we want to know how to actually work this out, how to model these. And the way we're going to model these are with 2 golden rules. The golden rules are, one, that the inputs, the non-inverting and the inverting inputs, have no current going into them. They have infinitely high input impedance. So there's no current going in. And secondly, number 2, the inverting and non-inverting inputs are at the same voltage. The output is going to do whatever it takes to keep the non-inverting and the inverting inputs at the same voltage. So let's look at how to use that. Here's an inverting amplifier on the left. You see that we've got our op amp in the middle. We've got the non-inverting port there hooked up E plus to ground. The inverting port E minus is connected to the node there between the resistors. And the output has a feedback resistor through RF. So we're going to start right here, EI minus E negative over ZI. Well, ZI is the complex impedance, and I'm actually going to call that RI for the time being. So that's just applying Ohm's law. And secondly, we know that the current going into this junction must be the sum of those two currents leaving the junction, based on Kirchhoff. And we know that this I minus should be 0 from our golden rules, which is why we've got EI is equal to, or sorry, II is equal to IF. That's our golden rule, and that's Kirchhoff. And then we can do on the output, we can do the same sort of thing. We can say that the E minus minus EO over RF, that's our ohm again. And we can connect these all together. And so with our second golden rule, we're going to say that the voltage at the inverting and the non-inverting ports is going to be the same. And because the E plus is connected to ground, we can say that they're the same and they're 0. So we can scratch those out. And so we get EO over EI is going to be negative RF over RI, or the output voltage is negative RF over RI times the input voltage. So it's negative, that's our inverting. It's got a gain RF over RI. And so we can always use this to amplify and flip the sign on a voltage. But what if we don't want to flip the sign on it? What if we want to keep a positive voltage positive or a negative voltage negative? We can use the non-inverting amplifier. We can do the same sort of analysis. And if you work through the same sort of analysis, you're going to see that the output voltage is going to be RI plus RF over RI times the input voltage, or 1 plus RF over RI. So what happens if RF is 0 and RI is infinite? Well, if RF is 0, that's just a wire. And if RI is infinite, that's like it's just missing altogether. And now you can see that the non-inverting amplifier with RF equal to 0 and RI infinite is just the follower circuit. That's our follower circuit. And if you go back to the follower circuit and you apply the same golden rules, what you're going to see then is that the output, EO, is going to be 1 plus 0 over infinity EI, which would just be EI. What if we want to make this a little fancier? We'll make low pass and high pass filters. Well, we're going to put a capacitor in there with the resistor. And so in the low pass filter, you're going to see that the complex impedance for the feedback path is going to be 1 over RF plus CF j omega. And so if we do exactly the same thing as before, we're going to get that the output over the input is negative RF over RI times this 1 over RF CF j omega plus 1. And so we get the same sort of gain here multiplied by the low pass filter. And the low pass filter is going to have a time constant of RF CF. If we do the high pass filter, exactly the same sort of thing. That input port, we're gonna figure out the complex impedance, which is going to be RI CI j omega plus 1 over CI j omega. And so if we work this out, the output over the input voltage is going to have this gain, and it's going to have a high pass section. So we could choose to design this in such a way that RF and RI were the same, and then we have just the high pass portion, or just the low pass portion, depending on which one we're dealing with. But there you go. You've got some basic op-amp circuits. You've got some amplifier circuits, and we should be all set to talk in class about computer systems and start talking about logic.